our approach here is application agnostic. It doesn't really care about voice or video. It's just providing a MOS estimate of the tunnel and the overlay in general. So you can apply this MOS estimation of performance to everything, to all your traffic. It combines three values, three discrete performance measurements that normally have to be assessed individually into one score. That's what I like. I want to show you that. All right, so you need 8.5, very low performance impact on the system itself, a little bit of additional disk usage. So from the user's impact, the MOS estimates are pretty low. This doesn't do a whole lot for them directly. If anything, it makes it such that the operator can remedy and prepare the network for their voice traffic a little faster. But from the operator's standpoint, it's pretty high impact, because it reduces the amount of time it takes you to assess the network and to diagnose readiness and network performance. MOS is an aggregation of several different values, right? It's an aggregation of latency, loss, and jitter in most systems, and it provides this ACR system, this absolute category rating scale that's rated from bad to excellent. The perceived performance difference between the scale ratings is not linear. So if you're from 1 to 2, the difference is it's just bad. From 2 to 3, it's just bad. Your voice doesn't work. But when you go from like 3.5 to 4, or 3.5 to 4.5, from fair to good and good to excellent, there's a very fast ramp in performance. There's a larger perceived gap between good and fair and good and excellent. My experience so far with MOS over the years has been that you need to be above 3, more like 3.2. Otherwise, people are going to complain. Anything above about 3.5 in most cases is good enough for most conversations. Now let's talk about this. So I've spent a pretty good bit of time with this feature at this point, and there's a couple of things I've noticed. All right, number one, take live view. All right, you're looking at live view. You're looking at your real-time overlay live view. You got 4 underlays, 2 high-speed internets, 2 LTEs. That's 24 performance indicators, because live view has 2 directions. People always forget this, but there are actually 2 different arrows here, and they are different, and they will be different. So there's 8 here, there's 12 here, there's 24. So right out of the gate, the MOS trends view takes 24 performance indicators and it aggregates them into 8. It's from this to this. Much, a bit easier to look at. So my point here is that what you'll find is that the MOS is a pretty good initial place to start. If somebody's complaining, they can pull up the MOS trends screen and they can get an at-a-glance view of periods in which performance was suffering. Then we actually take it further. We take those 8 underlays and aggregate them into an overlay MOS score. And this also works quite well. So, in this case, we've got those 4 different underlays over there providing individual scores, and then this gets bubbled up into a single aggregate value for the overlay itself. So we went from like 24 indicators down to 2. Here we've added MOS to the health map. And in this case, I've selected all underlays up here at the top, and we get a nice quick view of MOS problems across our entire fabric. Now here's the cool part. Let's switch it. So we're going to go from underlays to real-time. The real-time is an HA overlay. Notice the difference. Pretty neat, right? And so some of you guys might say, well, look at Wakefield Thompson. It got worse. See how it got much worse with real-time? That's because that's Wakefield Thompson B, which is an LTE device that doesn't have enough bandwidth to handle the HA traffic. So some of these sites that you'll see that there are some sites that worked better with just from the underlay perspective, but when you look at the HA view, it's worse. And again, this goes back to what happens with HA mode and the fact that you're doubling the traffic and bandwidth matters with HA.